Hey there, welcome to Kung Fu Physics, and it is the Memorial Day weekend of 2012. I don't know what you are doing, but it's hopefully something fun. I am going to be answering another physics problem off of the Physics GRE, which is, of course, a lot of fun. A lot of fun. The one I'm going to be doing is the off of the 1992 exam. It's number 66. And it looks something like this. Hopefully you can get that out and follow along. It's a mechanics problem. It's pretty easy to do without too much fuss and muss. I think maybe there's a couple ways you could get confused on it, but let's go ahead and get right to it. As usual, I glance at the answers. It shows me a bunch of energies in joules, but there's not too much to notice other than, I guess one thing you could notice is that A and E are quite a bit different in magnitude, and maybe you could make some kind of elimination off of that. But let's go into it. Number 66, a thin uniform steel chain is 10 meters long with a mass density of 2 kilograms per meter. One end of the chain is attached to a horizontal axis having a radius that is small compared to the length of the chain. If the chain initially hangs vertically, the work required to slowly wind it up onto the axle is closest to. Okay, so we have two situations, and I'll put them on either side of my board here, initial and final. And initially we have the small rod here and the chain hanging down. I'm going to put in arrow here to represent how far that is, 10 meters. Okay, so that's our chain hanging down 10 meters. And then the final situation, of course, has the little rod there, and the chain is all wound up around it. This is a small rod. We can basically look at this final situation as all the mass concentrated right there in the same place. So we're going to use conservation of energy, and we're looking at the potential energy. And so the potential energy is going to be higher in this situation, and the question is just how much higher it's going to be. And that is the precise amount of work that was needed to transform this situation into this situation. Because if the potential energy is higher here, then certainly work had to be done, and the work is being done by the bar that is rotating. That is a little bit different to me. I don't recall doing any freshman physics problems unfortunately where you had something like a rotating axle doing work for no good reason. I don't know, maybe they're just not that popular. But of course something rotating is going to do work just like a force pushing something over a distance, where you calculate the work, you know, is force dot the distance. There's ways to calculate the work done by something like this that would be rotating, and I'm sure they're very, very similar. But in this case, we don't really have to do any of that. All we have to do is reduce this situation to something similar, and really all we have to do is break this down so that rather than have this linear distribution of mass, we sort of imagine this as being a point mass. And where is that point mass located in our initial situation? And then we can very readily see what it takes to move that point mass and what height we have to move that point mass to reach this final situation. So in the final situation, I'm claiming that the potential energy is going to be mgh, and h is going to be the height that we have raised it, and that's the total amount of work that we've done. So what is h? How much have we raised it? And for that matter, what is m as well? Well, to get m, all we'd have to do is multiply the linear density of the chain multiplied by the whole length of the chain. That gives us the total mass. That's not that hard. G, again, we're going to use as 10, of course, and then h is going to be the height that we've raised this mass. So we need to simplify this, and if we could, as far as energy is concerned, let's get big M first, and big M just equals 10 meters times 2 kilograms per meter. Okay, so that's what I'm leaving off my naked numbers there without their units, but I get 20 kilograms for the whole chain, right? Okay, so 20 kilograms. Where's the center of mass located of this thing? Shouldn't be too hard to visualize. The center of mass is going to be right here, and so I've got a mass that's 20 kilograms, and if I imagine that being right there, it's halfway through. So this distance is just 5 meters, like so. So from a conservation of energy standpoint, there's no reason I can't shrink that down and imagine all of that mass being located at the center of mass there, 5 meters up. So to me, this is the way that I see the problem in my head. This is the fastest way to get there. There are other ways to do it. You can actually use the calculus and you know, integrate over this whole thing. I guess I'd have to think way more about that than I want to solve this problem. But the way that we're setting it up here is going to give us the right answer, and in my opinion, it's the more correct way to do it because it's faster. And as long as it's conceptually valid to do it this way, then there's no danger in doing it this way. So we have 20 kilograms located down here 5 meters beneath the final situation. And so in our final situation, if we say that the energy is 0 here, the energy is 0, and the final energy is all potential energy, and it is of magnitude mgh, where it's 5 meters higher. So we've taken that chain, and again, in our head, we're just imagining it as a mass of chain that's of weight 20, and we've moved it up 5 meters in the final situation. So of course, that is the work that's been done. We had to move that chain up 5 meters, and this is the value of it. So we take 20 times 10 times the 5, and that gives us it's 200 times 5, so it's 1,000, and that would be in joules. And that's one of our answers. So as you can see, they try and trick you a little bit by the value. You could screw up by not realizing that the center of mass is halfway, and you could screw up by saying the whole chain gets lifted up 10 meters. I think one of those answers is in there to sucker you into thinking that. But C would be the answer that we want. It's 1,000 joules, and that's the problem. I don't think there's too much more to say than that. Just having a really good understanding of conservation of energy lets you solve this problem pretty easy. So that's all I'm going to say, and study hard. See you next time.